what do we do at modeling? Why do we have models? Why are we using them? Well, they're developed mostly for water distribution system applications, but the hydraulics in there are good for a lot of other things, such as raw water lines, pressure irrigation systems, fire protection systems, sewage force mains, different industrial applications, cooling water applications, and a lot of things, you know, that you could use these hydraulic models for. So what we're doing during the course is going over the principles of hydraulics, talking about the concepts of flow, velocity, pressure, continuity, energy, and minor losses and things of that sort. So we're going to go through just the basics, because when you push that button that says compute my model, something happens. And we're going to show you what goes on behind the scenes, you know, because you don't see a lot of these equations, you don't see much of this stuff, but it's not just magic though. There's good sound science that goes into these hydraulic models. Okay, so fundamental concept, most fundamental one we deal with is flow. And what is flow? It's the volume past the plane per unit time. Now, how do you measure flow? Well, there are a lot of ways of measuring flow, a lot of units that people use. You would think that what would be the correct unit of flow? The correct unit of flow, if you're really following the rules of science, should be cubic meters per second. Yet, even in metric countries, they don't use that for water systems. Why would that be? Well, it's such a big quantity. A cubic meter per second is a lot of flow. And so we'd be dealing mostly with numbers like 0.002, 0.017, you know, these really tiny numbers. So usually even in metric countries, you're dealing with liters per second or cubic meters per hour, something like that. Now, for here in North America with our backwards English units system of units, we deal with cubic feet per second to be the correct units. But we don't do things for the correct units. We use a thing called gallons per minute for the most part. So that's the default in our hydraulic models, because that's what water engineers have come to use over the years. So GPM is most likely the units you're going to be working with. Although another common one when you get into large flows is million gallons per day. So even though cubic feet per second is the correct one in the foot-pound second system, we use a variety. If you're working with irrigation systems, they're going to be talking about acre feet per day. And if you really want to get old-fashioned, you'll be talking about cubic furlongs per fortnight. You know, there's a lot of ways that flow is measured. The next concept we've got to review is velocity. Now, velocity is the speed the water moves through, and we have a nice equation that relates the speed that the flow moves through a pipe in terms of, you know, flow per unit area is velocity. So if you know the flow and you know the area, you can calculate the velocity. And it's usually pretty straightforward. Usually we use feet per second or meters per second. There's very seldom you're going to hear miles per hour or something like that as a velocity unit. So that's velocity. Now, the question is, what's the right range? Now let's think about this. What should the velocity be in a water main? What do you have if you went out in front of the building you're in and dug up the pipe and measured the velocity? What do you think the value would be? Okay, well, for most water systems, we're usually talking about flows on the order of maybe 1 foot per second. If you're in the neighborhoods that are residential, you're probably talking about 0.2 feet per second this time of day, because those pipes are really sized for fire flows, and most of the time we're way below fire flow. Okay, so we're usually talking about numbers in the, you know, point something feet per second as a typical number in typical water distribution systems. You know, as you get into the bigger transmission mains, usually they're flowing at a pretty good clip. They might get, you know, 3, 4, maybe even 5 feet per second on an average day. If you start getting above that, what happens? Well, you start getting a lot of head loss. You start using up a lot of energy. So the faster the water goes, as we'll see in some other equations, the more energy you're using, which is more pumping you got to do. So usually keep the flows, you know, when you're designing systems, somewhere 5 feet per second or lower, even during peak flow times. But it depends. Some people will say 10 is okay, you get up to it. You know, some people use 8 as an upper limit. It really depends on the standards that you're working with. Another problem when you get really high velocities, and we're not going to cover this in this course, but we could have a lot more problems with hydraulic transients when you change the velocity. So in the velocity high, you could get hydraulic transients, which are water hammer events that can burst pipes if you're not careful about them. So we tend to stay away from those really high velocities, partly for energy, partly for transient reasons. But as I said earlier, you know, in some of these residential neighborhoods, you could have some very low velocities because the pipes were sized to carry flows that very seldom happen, unfortunately. Well, fortunately, we don't have a lot of fires. Okay, so if you think that flow and velocity had a lot of units and might be a little bit complicated, you haven't seen anything yet. Now we get into pressure. Okay, what's pressure? Well, it's what you feel when you have a report due tomorrow morning and you're only about halfway through and it's time to go home and you're not done yet. But that's not the kind of pressure we're talking about here. We're talking about force per unit area. So this is the force that the water exerts on the pipe. It's pushing out, trying to break the pipe. Okay, so if I ask you now, what's the correct unit for pressure? The correct unit for pressure is the Pascal. But if we did a show of hands in the class, probably no one uses the Pascal, which is a Newton per square meter. And the reason we don't usually use it is because of the opposite reason we don't use cubic meters per second. A Pascal is a very tiny amount of pressure. And we'd always be talking about, 75,000, 682,000 pascals. Yeah, we're talking about these gigantic numbers. So usually in metric countries, you'll be working with kilopascals or possibly bars even, where we're talking about just 4, 5, 6 bars of pressure. So there's a variety of units for pressure. Of course, in the English system, the correct unit for pressure would be pounds per square foot. But do we use pounds per square foot? No, we use pounds per square inch because that's a number that we've always used. So that's why we use pressure in PSI, pounds per square inch, is almost always what you're going to see if you're talking with an American water utility. Ask it, what's the pressure? You're going to say it's 36 PSI, maybe something like that. Okay, so if we have those numbers, then we also can talk about pressure in terms of atmospheres. An atmosphere is 14.7 psi because that's what you'll feel if you're just standing outside around sea level. That's the amount of pressure from the air above you. So how many times the air pressure is the atmospheric pressure? But pressure gets even more complicated because are you measuring the pressure relative to the atmosphere or are you measuring the absolute pressure? That is the pressure including the atmospheric pressure. Now generally if we have a typical pressure gauge, in typical water systems, you're going to be using gauge pressure. Okay, so it's the pressure above atmospheric. So if the pipe is dry, it's 0. If you're using atmospheric pressure, if the pipe is dry, you've got about 14.7 on you. Now, absolute pressure does come in handy when we talk about vaporization when we get into hydraulic transients. But for the most part, we deal with gauge pressure when we're talking about pressure in water systems. Then every once in a while, especially talking with old guys who are water systems operators, you're going to say, what's the pressure? They're going to say it's 40 pounds. And you say, pounds? How could pressure is not a weight? How do you deal with pounds? Because that's what they've always done. That's why they talk about pounds of pressure. And so you just got to deal with that. Now, pound, it kind of can lead to some misconceptions. I heard a story one time where this guy decided he was going to save gas in his car, so he was going to let couple of pounds of air out of each tire, and that way his car would be lighter. So hopefully you see the fallacy in that argument and a reason you shouldn't say pounds when you're talking about pressure. You should say pounds per square inch or PSI when you're talking with somebody. But people do use pound a lot, so just be used to that. All right, but that's not enough. We have to have more ways of measuring pressure, because often we'll talk about pressure in terms of the height of the water column that pressure can support. Okay, so that means that if you have 20 psi, you're talking about 46 feet of water above it will equal 20 psi. Okay, we'll talk about, sometimes we'll talk about pressure in terms of the height of the column of mercury in millimeters that you can use. But generally we talk about feet of pressure head. It's usually the way we talk about that. And people will say we've got 40 feet of head here or so. The conversion factor, for those of you working in North America, it's 2.31 feet is 1 psi. Just memorize that number, okay? It's something that comes up all the time when you're working with hydraulics. So if you don't have it memorized yet, memorize it now because, I find myself doing that conversion from feet of head into pressure units all the time. So it's just a good number to work with. Now, this pressure doesn't matter the volume of the tank, whether you're 46 feet below a narrow column of water or you're 46 feet below the Atlantic Ocean, it's still 20 psi, the pressure. The only time that would change is if you're in such a small tube that its capillary effects come in, but we're not dealing with those. So it's basically doesn't matter how big the water column is. It's just how deep you are under it. And in metric countries, we have similar conversions between kilopascals and a meter of water. So a tenth of a meter of water is about 1 kilopascal. So you get those kind of units. So as I said, the diameter of the tank that you're under doesn't really matter. It's just the force that comes down per unit area is the same. Okay, so what should the pressure be? Okay, so what would we consider to be good pressure or bad pressure? Let's talk about these in terms of PSI. So what's the usual minimum pressure that we accept in our water systems? Well, number you'll hear most often as a minimum is 20 PSI. And that's how you evaluate fire protection systems. It's what flow you can get out of the hydrants at 20 PSI. Now, why 20? I mean, because all you want to do is keep the system pressurized, right? You just want to make it so that you don't have water from outside the pipe leaking in. You got to keep it pressurized. So you need a positive value. Why do you think they pick 20 as the usual standard in most places? Well, the reason that I've heard is the best explanation is that most buildings are 2 stories high. That's just a very typical. You still want good pressure on the second story of the building. So if you want that, you've got to have about 20 PSI in the water main in the street. So that's the most common accepted reason why we have 20 as a standard. If somebody's got a better explanation, I'd like to hear it. But a lot of water utilities don't really want to design their systems for 20 PSI because that's pretty low. I mean, if you had 20 PSI in the street, your shower on the second floor would not be very satisfying. So most water utilities set some other design target that they really design the system to work at 30 PSI or 35, and they'll accept 20 during a fire or another emergency, but they really design it for some higher pressure. So that's what you'll see. These numbers aren't nearly as uniform as that 20 PSI minimum. You'll see various utilities use various numbers. Now, there's also some research in recent years that have been arguing the case that keeping the pressures high is really bad because it accentuates leakage and causes more pipe breaks. And so there's a good bit of research in the area about what should the lower number be, because the higher you have it, if you do have a leak, the more it's going to leak. What about maximum pressure? What should the maximum be? Well, this is even a less precise number. I mean, people will say, oh, we don't want it above 80 PSI, and so that's not a reasonable value, but you're going to find places, especially in hilly areas, where the pressures are 100, 125. Usually a more rigorous upper limit might be 150 PSI as a real upper limit, because usually that's where water heater blow-offs open up and they start letting water out and popping off these valves on top of water heaters. So sometimes people will use that as an upper limit, but that's a really high value. So what if you have higher than that out in the street and you're hooking up a house? What do? Well, usually you would not design your water system to have 180 PSI in the street, but if you do, usually you have a pressure reducing valve between the water main in the street and the house to keep the pressures in a reasonable range. Plus your plumbing fixtures wear out faster if you have a really high pressure. Okay, so those are some of the basic concepts you're going to be seeing throughout the course, and you should have seen these already. This should have just been a review of some of the basic fundamentals, but hopefully give you a little reminder and refresher on these kind of basic values. Okay, so now we're going to get into some of the principles that are solved. What are the rules that are used by the computer program to solve pipe network equations? Or what are those pipe network equations? Well, there's just 2 fundamental principles that we use. The first one is the continuity principle, and this is pretty simple. Mass in equals mass out. If you have a junction of pipes, the total mass of water into that junction is going to equal the mass out. If it didn't, we would have mass created or destroyed, and we'd have nuclear reactions, and you really don't want that happening in your water system. So it's a very simple principle. In our models, we say that the sum of the flows into any junction node equals the sum out plus any water used by customers at that junction. So that is the principle. So it's very simple, and it's a nice equation. It's linear. You see, there's no exponents. It's a nice equation. We like working with equations like this. When we get involved with tanks where the water levels could go up or down, the equations we solve inside your hydraulic model are basically the net flow into the tank is equal to the change in elevation times the area. So it's pretty simple, the continuity principle. Now, the next one is the energy principle. And while that one was simple, this one gets a lot more complicated because energy can be in many forms. The 3 most important ones, as far as piping hydraulics are concerned, are the three that I show up there. Okay. First term is the elevation. Higher up in the Earth's gravitational field the water is, the more energy it has in terms of potential energy. Second term in the equation is the pressure. So the pressure could be in terms of elevation or pressure. And the pressure term is P over the weight of water. Or it could be in terms of kinetic energy, which is measured as V squared over 2G. So the energy in water systems can be converted as it goes up and down hills from elevation head into pressure head. And we tend to use the word head for energy. Now remember, what's the correct unit for energy? It's joules, right? But we don't use joules. We use foot-pounds of energy per pound of water. That's what we use, and we call it head. And we'll use head a lot, or we'll also call it the hydraulic grade line elevation. If you add up all these quantities, you get the elevation of the energy grade line. Now, among these terms in the equation, not all of them are really as important, because usually the velocity head is pretty negligible in water distribution system piping. There are a couple of cases where we have to consider it, but in most cases, V squared over 2G, let's say a high velocity is 8. If you square 8 divided by 2G, it's only 1. While the pressure head might be 100, and the elevation might be hundreds of feet, the velocity head is usually not important in most of our water distribution calculations. So we got some fundamental concepts related to energy then. We talk about the hydraulic grade line, that is the pressure head plus the position in the Earth's gravitational field. So it's pressure plus elevation. And we call it the hydraulic grade line. I'll show you a graph of that. The total head actually consists of the static head plus the velocity head. But I said the velocity head is pretty small in most cases, so the total head and the velocity head are generally about the same. And head loss is the difference between the head and 2 points. Okay? So we asked the question, I shouldn't show the answer here, but it's, where does water move in a water system, in a pressurized piping system? It doesn't necessarily move from high elevation to low elevation. It doesn't necessarily move from high pressure to low pressure. Instead, it moves from high head to low head. Okay, that's the direction the water flows. And to visualize it, we might look at something like this, where the hydraulic grade line is the elevation of the pipe plus the pressure head. And the water would, in this case, go away from the tank, where it scoots down the hydraulic grade line. So if you're to measure, the elevation of the ground plus 2.31 times the pressure at the ground level, you'd get this point. And the point would decrease in the direction of flow. And what's causing this decrease, of course, is energy loss. And why does the energy get lost? Well, friction along the pipe wall and drag and obstructions like partly closed valves cause the energy to be lost. So the head loss is this using of energy to move the water from point A down to point D gives you the head loss. So that's not too hard of a concept to master. The hard part is, how do you calculate it? Because in laminar flow, it's pretty easy. You can actually go back to F equals ma and the first principles of flow, and you can understand and calculate what the head loss should be. In turbulent flow, though, there's no single theoretically correct equation you can go back and say, this is derived from the fundamental laws of nature. There's some empirical coefficients in any head loss equation for turbulent flow. Now, the main ones that are used in the water industry, Darcy-Weisbach equation, remember that from the basics you had in fluid mechanics. And the problem with Darcy-Weisbach is you got to get the friction factor. And we'll talk about that in a later slide. And there's many methods to calculate the friction factor for Darcy-Weisbach equation. Most commonly used one, though, is the Hazen-Williams equation. This is in some ways it's a simpler equation. In some ways it's more complicated. And we'll talk about Hazen-Williams, which is the most widely used, at least in our part of the world. And Manning's equation is also used. It gets used more so in sewer force mains, where the people working with sewers tend to like Manning's equation. Okay, so Darcy-Weisbach equation looks something like this. It's a function of how much head loss you have. Depends on how long the distance you're going, how fast you're going, and how big the pipe is. And all those are nice measurable things. The thing that's not very easily measurable is this F, the friction factor. So what is the friction factor? Is it like 0.1? Is it 3.14? Where's the friction factor? Well, the guys who were studying this had a lot of trouble because Darcy-Weisbach came up with this equation about 1850 or so. And for the better part of the next century, there's a lot of research done on what is F, because you would measure F in one situation, you get the value, you measure it somewhere else, you get a different value. And it was a very difficult problem that people looked at for years. It was really the rocket scientists, the German rocket scientists under Prandtl back around the turn of the last century, came up with some very interesting experiments where they would do things like glue sand grains on the insides of pipe, and they'd run water through those sand grains and figure out, depending on the size of the sand grain, how much the value of F changed. And it was some really interesting research that went on, and from these really smart people that developed these things. So they came up and they found out that the value of F depends on the form of the roughness, how big it is, and the shape. It also depends on the Reynolds number. Remember the Reynolds number? It's an indication of the relative importance of viscous forces to inertial forces. And so they found out that the friction factor depends on the pipe roughness and the Reynolds number. And unfortunately, for any pipe, it really is a function of how fast the water is moving as well, in addition to the V up in the first part of the Darcy-Weisbach equation. And a guy came up about the 1940s or so, a guy named Moody at Princeton University came up with this graph that kind of showed how to get the friction factor. And you see it's a function of how rough the pipe is, that's the right axis, and what the Reynolds number is on the bottom axis to get the friction factor. And those of you that had to do homework problems doing this by hand thought this was kind of a tedious thing to go through, but you had to pick the roughness, pick the Reynolds number, and that intersection, you would trace it back, and there would be that would be the line corresponding to that pipe, and the roughness here would be read off the vertical axis. So it was tedious, and people, didn't really like it that much. It's widely accepted around most of the world, but Americans tend to be a pretty practical people. They wanted something simpler and easier to use. And two researchers around 1900, Hazen and Williams, came up with this equation, which in some ways isn't as nice as Darcy-Weisbach because it's got a nasty exponents on some of these terms, but it tended to work better. And the good thing about this equation was the Hazen-Williams C is relatively constant. Unlike F, which varies all over the place, Hazen-Williams C-Factor tends to be constant, more or less. There's a lot of caveats into that as well. But it's a pretty good parameter to have. So people like this, and they still use Hazen-Williams a great deal. So it really depends on, how much carrying capacity the pipe has, which is how, so it's not a measure of roughness as the Darcy-Weisbach F is. It's a measure of carrying capacity or smoothness of the pipe. And you can measure this with tests in the field or back it out during your model calibration. The difficulty with this is just that it is not always known ahead of time. And it's one of the things that we have to adjust sometimes in our modeling work. And the other thing that happens to this, especially with unlined old cast iron pipes or metal pipes in general, is that they corrode inside. And they form these nasty looking tubercles inside the pipe, which are kind of like growths of corrosion products. And they tend to cause C-factors to change over time, as well as roughness in the Darcy-Weisbach equation. So what are typical values of the Hazen-Williams C-factor? What should you use? What do you use these days? Well, as I said, it tends to vary a lot. Very smooth pipes, ideal conditions, you might get a value like 150. A lot of people use for design are numbers like 130, maybe down to 110 or even 100 or so, depending on the type of pipe, material, and age and such. But I've seen pipes in real systems that have C-factors down around 100, where they're very corroded pipes, a lot of junk on the inside of the pipes that has grown over the years. And so generally you'll look up some tables like this of different types of pipe when new and at various ages of the piping. And there's a lot we have in our textbook. We have a whole bunch of tables like this for different values of C-factor because they don't change too much in the short term and they don't vary with velocity very much. There is some variation, but not too much. Okay, the final equation to talk about is Manning's equation, which looks like this solved in terms of velocity. And it's basically a function of just the units conversion factor, the hydraulic radius, which is the cross-sectional area divided by the wetted perimeter, and how far you pump in, how much head loss, what the hydraulic gradient is, this H over L, and then an N value. So N value is a roughness value for the Manning's equation. And Manning's equation, again, has values of N published. Nice, smooth, straight PVC pipe might get 0.009. Ordinary concrete pipes about 0.013, and that's a value that you'll see used a lot in sewer design work. It's kind of a conservative number that people use in sewer design work. But you could show that really new smooth pipe is a lot better than that 0.013. In sewer flow, you don't lose Manning's N as fast as you lose roughness in water pipes. So, people generally have kept the values they use in this range. And you can convert back and forth between C-factors and Manning's N. But the conversion depends on the size of the pipe and the velocity, because the exponents in those equations are not the same. So there's not just a single conversion factor from one to the other. Okay, having talked to you about these three different head loss equations, which one is right? I say that with a smile on my face because they're all sort of right, and they all have their strengths and weaknesses. Okay, so we take these three equations, and let's look at their strengths and weaknesses. Darcy-Weisbach is good because the viscosity and density of the fluid are explicitly considered, and you can use them for all different kinds of fluids. While Hazen-Williams and Manning are really water equations. They're not really intended for, whether you're pumping kerosene or wine or whatever you happen to be pumping. Manually, though, it's hard to get F with Darcy-Weisbach. It's relatively easy to calculate, to know C-factors or N values for Manning's equation. Hazen-Williams really is mostly relevant for very smooth flow conditions, while Manning's is more for rougher flow, and Darcy-Weisbach covers the whole range a little bit better. Now, in the U.S., not too many water engineers use Darcy-Weisbach. Overseas, we see it used a great deal, but we've just gotten used to Hazen-Williams, which is the most commonly used one in the U.S. Manning's you see more in sewer-type flows. Okay, seeing all that now, we now know everything there is to know about calculating head loss. And the answer is no. There are things called minor losses. Now, what are minor losses? Now, anybody who says that their losses less than 21 years old are wrong. They're losses caused by things like bends and fittings, joints, valves, things of that sort. So these minor losses are generally described by a minor loss K coefficient, which is the minor loss coefficient. And you can look these up in tables. They'll give you values that you can use. Now, the good thing about this in most water distribution system modeling is that most gate valves are wide open, and the losses at bends are pretty small compared to the pipe barrel losses. So minor losses are often ignored in a lot of the water distribution modeling examples. But if you're in systems where the length of pipe is small relative to all these fittings, you can calculate the minor losses, and we give you tables of K values, and there are a lot of them published in the literature if you don't have them in one of these tables. And the model calculates this sort of thing. Sometimes they give you loss coefficients, not in terms of K value, but a flow coefficient, which if you're working English units, it's kind of what flow you get through it at a 1 psi pressure drop. Okay, and you have to use a conversion like the one we have here to go between those coefficients and the K values. Because one of the things that happens is the K value for a given body of a valve, whether you scale it up or down, the K value doesn't change much. While the C sub V, these flow coefficients, are very much a function of the size of the valve. The K value doesn't change very much. Okay, so that's nice if we have our water systems are one pipe going from point A to point B, but real water networks are much, much more complicated than that. Okay, so the way we have to represent these things inside of hydraulic models are a series of links and nodes. Okay, links are essentially pipes, but they could be other things I'll explain. And nodes are places where things happen. They're usually intersections. They're places where water is being consumed. They're the location of tanks or pumps or valves. So links connect nodes. So to have a true model, you must have nodes and links. And this is the representation of it within the hydraulic model. So nodes are things like junctions, tanks, reservoirs. Links are things like pipes. Now, pumps and valves are have properties of links and properties of nodes, because pumps and valves are generally point features in your GIS, but they really have two heads. Like a node usually has a single value for the head, the hydraulic grade line, but pumps and valves are things that change the head at a point. Okay, so hydraulically, they're links, but the way they're represented in the model are nodes because they are really points. Now, some computer models treat pumps as links, which in some ways is good, but in some ways it's really bad because they don't look like pumps when you do them that way. So in our models, pumps are point features. Okay, and so are control valves or isolation valves as well. So the thing about the modeling, though, is solving the head loss equations. So for every junction you have in your water system, there is a continuity equation, a mass in equals mass out equation. For every pipe, there is a head loss equation, whichever of those head loss equations you use. So there are a lot of equations. There are, in many water models, we have 20,000 junctions and 30,000 pipes. So you got 50,000 equations. And the head loss equations are nonlinear, which is a bad thing for solving numerical equations. So you don't want to calculate pipe networks by hand. It would be very, very time consuming, very, very difficult. Instead, what you do is you use a computer model where the size of the model can be very large, and you calculate systems that manually you just could not calculate by hand. There's no way you could solve a 10,000 pipe model. If you started today, you might get it done before you died, but you'd be welcoming death if you were calculating the model that long. So this is where computer models became very, very popular and important, in that in the old days, engineers working on these models had to make a lot of assumptions. They had a lot of simplifications, and they got by all right. Usually the rule was, when in doubt, build it stout. If you didn't know what the answer was, guess a higher value, And we can do a much, much better job now, both in design and operation of our water systems, and predict the flows and pressures very precisely because we let computers do the dirty work. Let them solve those thousands of equations. And that's the thing that computers do very well. They're sort of idiot savants. They don't really think, computers, but they can calculate really fast. So we let computers do the dirty work. We have computer models like WaterGEMS and WaterCAD to do that kind of thing. So what actually happens when you hit the compute button? Well, what we do is you take the data that you've entered describing the pipe network, and we set up these n equations with n unknowns. One equation for pipe and junctions, and we guess at an initial solution, essentially. We have a good algorithm for that. And then we solve these equations. So you solve for the correct, a better value of head and a better value for flow. For each junction we calculate a head, for each pipe we calculate a flow, and we see, does it stay the same? If it stays the same for 2 iterations, then we've got an answer. It's converged. If not, we go back and modify those solutions over and over again. Some models, you can do this in 2 or 3 iterations. You get a great convergence. And others, it takes a lot of steps to do it. And then once you've got the basic parameters, the head and the flows, you go back out and calculate pressures and velocity and other things that are essentially secondary variables that you've calculated once you know H and Q. And then we present the results. And that's how a steady state model, which is basically a snapshot of what's going on at time, is calculated. But there are a whole variety of other modeling applications that we have. Okay? And a typical, so steady state model is the simplest kind of model, and that's what we're going to learn in the first workshop. But then we want to see, how does the model behave over time? And that's where you get into extended period simulation, where you watch flows changing as the water use changes over the time of day, and pumps come on and off, and tank levels go up and down. But then once we have these solvers that can solve pipe network equations, we can do all sorts of things. We can track water quality through a distribution system. We could look at what the fire flow is at every point in the distribution system. We could do various kinds of optimal design and operation. And we could go out and plan flushing programs so that we get effective flushing of our water systems and understand what's going on when we open up those hydrants to flush the pipes. So there's a lot of different things that you can do once you get. This is just a few of them. We have energy analyses, we have criticality analysis. There's a lot of things you can do once you've built your model and believe in the calibration of the model. So that brings us to the end of our talk on the principles. And if you're going to work at real pipe networks, you need numerical solutions, and that's where hydraulic models like WaterGEMS are just so valuable and make your life doable and give you power that engineers 50 years ago just couldn't figure out how to do some of these problems. They're very challenging, that are now pretty easy.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.